Okay, so let's welcome to a lesson about Hooke's law. Robert Hooke was a British physicist at the 1900s century, and he have done many things to the physics society, but one of the things was Hooke's law, and that is an investigation and a statement about the relationship between forces and the stretch of a spring. I will show you what that means. So, Robert Hooke had a spring, and he exerted for a force like this, and he looked how much the spring was stretched, and he thought, is there any relationship between the force and the stretch? So you can do like this. You take a mass and you have it on the spring like this, and of course you need to have it in this direction, but then you don't see what I'm doing. So if you have a spring and you attached a mass to it like this, it will stretch. And if you have two masses like this, it will stretch even more. And if you have three masses, it stretch even more. And you can do it so in that way for a while until the spring is broken. But I have done the research at the exact way, same way as Hooke did for 150 years ago. So let's look at it. We need a table to see the relationship between force measured in Newton and the distance that the spring stretch. Distance in meters, like this. So, when I did it, I realized that with no force attached to it at all, there was no stretched distance. It is like this. So you see, there is no distance to measured, because you start here now, like this. And when you have the mass, it will stretch. So if it's stretched like this, you have to, now let's see if I release it, it goes up. But with a certain force, you have a certain distance. With another certain force, you will have another distance. So this is the measured distance. Now, with no force, there is no distance. With 1 Newton, because I had 100 grams, so 100 newtons will give me a force on 1 Newton on the surface of the Earth. Then the distance was 0.04 meters. Okay, don't need meters, I have it here already. With 2 masses with 100 gram each, that's 2 newtons. Then the distance, the stretch for the spring, was 0.150 meters. Well, the force is doubled, and the distance is also doubled, almost at least. With 3 Newton, the distance was 0.221 meters. And with 4 Newton, the distance was 0.295 meters. So what Hooke realized and saw is that there is a relationship, a very nice, beautiful relationship between the force and the distance. If I have a force, there will be a distance. If I double the force, the distance will be doubled. If I make the force 3 times bigger, the distance will be 3 times bigger. So we see that they are proportional to each other. Now, I can show this relationship in a graph. So, graph. We have a y-axis like this and an x-axis like this. And now you see the force gave me a distance, but I could go the other way around. So now I will have the force on the y-axis. Normally this is the dependent variable, and this is the independent variable. Now I change it, but it doesn't matter. Newton and distance in meters. And I have 0.1 meters here. So this is 0.2 and this is 0.3. 1 Newton, 2 Newton, 3 Newton, and 4 Newton here. So 0.074, it's somewhere here, and then you have 1 Newton. 0.15, it's here, and you have 2 Newton. 0.22, it's here somewhere, so you have 3 Newton. And this is a little bit smaller than 0.3, and then I have 4 Newton. So you see the pattern. You take your ruler, you know, the teacher don't need a ruler because they've worked so long, but you use it, and you see the relationship is a straight line. So it's a linear function that describes the relationship between the distance and the force. So now you can make prediction with this graph. If there is a mass attached to a spring and the distance is somewhere here, then you can say what the force probably is attached to the spring. And if you use the force that's 2.5 Newton, then you can, without put it on the spring, telling the length of it, the stretch of it, when you put it there. Okay, a linear function through origin like this. We know the formula that describes this relationship. The force is equal to some constant times the distance. And now this distance, we call it delta x, the change in distance. That's the stretch. So it's y equals kx from the maths lesson. And this constant k is called the spring constant. It's a constant that depends on different springs. So this is a spring. You need a force to stretch it. If it is the spring that holds up a car, then it's a very strong spring, and you need a very strong force to make it move. And you need that strong spring because the car is so heavy. And if you would like to calculate the spring constant, you need to take the force and divide it with the stretch, the change in x. And then the unit for the spring constant is Newton per meter. You can have Newton per centimeter also, or millimeter, or any unit here, doesn't matter. Now, if I have a spring and I pull it, I use a force on it like this, I'm doing a work because I use a force and a distance. So you already know that work is a force multiplied with the distance. But you see, which force will I use? Let's say that I use finally the force like this. So I would like to calculate a force when the end force is like a little bit more than 3. You see, at the beginning, there is not any big force I have to use. And the force is getting greater and greater, and I have to pull more and more. And you can see it because the force is proportional to the distance. That means the longer the distance, the greater the force. So at the beginning, when the distance is small, the force is small. And at the end, the force is quite large. So, therefore, I take the force, I multiply it with the distance, but I have to divide with 2. So, force divided with 2, that is the average force. So if I finally use this force, the average force is between the final force and the starting force, that's 0. So if I do a work, is my work gone when I've done this? No, it's not. I can use it for something like this. If I use it, a work like this, and then I release it, you see, I got a motion. So something is moving. So my force will becomes a potential energy. It's potential energy in the spring. It has the potential to do something, to moving an object, like a mass is like this. If the mass is moving, there is a work done on it. And now the spring is doing the work, so it has a potential. And the potential is the same as the work done. So I rewrite this. But now, instead of the force is equal to K times delta X. So instead of force, I write K times delta X. And then I multiply with delta X again. That is 2 delta X multiplied with each other, or delta X squared. And then you divide with 2. So this is the formula for potential energy in a force. So you square it, and we write potential energy in a spring. Depends on the spring constant. The greater it is, the more potential you have it in it. And the bigger length that you have put it, that you have stretched it, the more potential the spring have. It's like a bow and arrow, you know. If you use a strong force and you put it away like this, stretch it a long distance, then it has a great potential to shoot away the arrow. Okay, let's look on an example on this. The force 5 Newton stretch a spring 7 centimeter. Okay, I have to see it like this. A. Calculate the spring constant. Okay, if you know how to do it, you take a pause in the video, do it, and then you start again when you're done and see if we have the same answer. Okay, so spring constant. I write down the formula. It's the force divided with the change in distance for the spring, the stretch. And we have it like this, so it's no problem. So K is 5 Newton divided with, but I convert this to meter, so it's 0.07 meter. And that is equal to, so I use my calculator, 5 divided with 0.07. That is 71.4 with 3 significant figures, Newton per meter. That means that if you want to stretch this spring 1 meter, you need to use a force that's 71.4 Newton. 71.4 Newton for every meter. Okay, the second one. What is the work done? So, I don't know what it is that gives this force 5 Newton, but what it is doing a work. What is the work done? How many joules do you need to stretch this spring 7 centimeters with a force 5 Newton? Well, the work done. You can use this formula, or you can use this formula. It will give you the same answer. The work is the change in potential energy. I will use this formula. K is 71.4. That's my value for K. Multiplied with the stretch, and that is 0.07 squared divided by 2. Now it is important that this stretch, this length, is in meter if you want the unit to be in joule. If you have it in centimeter, you won't get joule. So the work done is, I use my calculator. So I have all the digits here. I don't round it off to 7.1.4 now. So I will multiply. So I just press multiply. Ons, that's that number. 0.07 to the power of 2 divided with 2. Enter. 0.175 joule. Okay, now you know a bit about Hooke's law and the relationship between force and stretch of a spring. Thank you.